Classical physics refers to theories of physics that predate modern, more complete, or more widely applicable theories. If a currently accepted theory is considered to be modern, and its introduction represented a major paradigm shift, then previous theories, or new theories based on the older paradigm, will often be referred to as classical. As such, the definition of a classical theory depends on context. Classical physical concepts are often used when modern theories are unnecessarily complex for a particular situation. Classical theory has at least two distinct meanings in physics. In the context of quantum mechanics, classical theory refers to theories of physics that do not use the quantization paradigm, particularly classical mechanics, including relativity. Likewise, classical field theories, such as general relativity and classical electromagnetism, are those that do not incorporate any quantum mechanics. In the context of general and special relativity, classical theories are those that obey Galilean relativity. Among the branches of theory included in classical physics are classical mechanics, Newton's laws of motion, classical Lagrangian and Hamiltonian formalisms, classical electrodynamics, Maxwell's equations, classical thermodynamics, special relativity and general relativity, classical chaos theory and nonlinear dynamics. Comparison with modern physics. In contrast to classical physics, modern physics is a slightly looser term which may refer to just quantum physics, or to 20th and 21st century physics in general. Modern physics includes quantum theory and relativity, when applicable. A physical system can be considered in the classical limit when they satisfy conditions such that the laws of classical physics are approximately valid. In practice, physical objects larger than atoms and molecules can be well understood with classical mechanics, including the objects in the macroscopic and astronomical realm. Beginning at the atomic level, the laws of classical physics break down and generally do not provide a correct description of nature. Electromagnetic fields and forces can be described well by classical electrodynamics at length scales and field strengths large enough that quantum mechanical effects are negligible. Unlike quantum physics, classical physics generally characterized by the principle of complete determinism, although deterministic interpretations of quantum mechanics do exist. From the point of view of classical physics as non-relativistic physics, the predictions of general and special relativity are significantly different than those of classical theories, particularly concerning the passage of time, the geometry of space, the motion of bodies in free fall, and the propagation of light. Traditionally, light was reconciled with classical mechanics by assuming the existence of a stationary medium through which light propagated, the luminiferous ether, which was later shown not to exist. Mathematically, classical physics equations are ones in which Planck's constant does not appear. According to the correspondence principle and Ehrenfest's theorem, as a system becomes larger or more massive, the classical dynamics tends to emerge, with some exceptions, such as superfluidity. This is why we can usually ignore quantum mechanics when dealing with everyday objects. Instead, the classical description will suffice. However, one of the most vigorous ongoing fields of research in physics is classical quantum correspondence. This field of research is concerned with the discovery of how the laws of quantum physics give rise to classical physics, in the limit of the large scales of the classical level.